And we're now doing the problem that says, we got 28 kids in the club, and they drink coffee or hot chocolate or neither. And we're going to draw a Venn diagram to describe this. Okay, so here's my group, my club of students right here, and there's 28 of them. Here are my two circles. I got coffee and hot chocolate. And right from the beginning, I know there's 6 kids out here. Right? Because 6 of them are not drinking coffee or hot chocolate. Now, 18 of them drink coffee. So the whole coffee circle is 18. And the whole hot chocolate circle is 9. Now we have a problem. Because how many kids is this right here? 27. So the circles have 27 people in them, but they can't because there's only supposed to be how many people in these circles? 22? In the circles, there should only be 22, but there's 27. What does that mean? Some of them are part of both circles. So if there's only allowed to be 22, but I have 27, I have how many extras? 5. That's how many people voted twice. 5 people got counted twice because there's 5 extras. All right, so what is that logic again? I knew from the given information there could only be 22 people in these circles. But there's 27. That's 5 too many.
So in the actual circles, there's 13 people who like coffee.
Well, the whole coffee circle is 18.
Yeah.
But this section of it,
Yeah.
which is the people who only like coffee, is 13. And then this is 9, but this section of it is 4. And now kids, look. What's 13 plus 5 plus 4?
23.
Exactly what it's supposed to be, right? Got those 22 and these 6, and that's how you get your 28. Answer the question. What's the probability if I grab a kid that he drinks only coffee? 13 over 28. Make sure you're putting it over 28, kids, because what always goes in the denominator? The total. How many kids are in this class? 28. All right, now we've got the athletes, and they're drinking Gatorade. And they drink blue Gatorade, red Gatorade, and white Gatorade. And I know that there are 50 athletes. 29 of them drink blue, 31 of them drink red, and 22 of them drink white. Am I going to put those numbers in my diagram? Burkhart, you with me? What are you doing back there? It's checking what?
Checking something exposure.
Okay, this isn't the time to be doing that, honey. Right now we've got Gatorade to worry about. You can check that in a minute. Yes, we're doing a Gatorade problem. Now, am I putting any of those numbers into my Venn diagram? No. Those are the totals. They don't go in the Venn diagram. What goes in the diagram is 11 like all 3, 5 like only blue, 10 like only red, and 2 like only white. Those numbers I can put in because they have sections in the diagram, right? Now, I have the same 3 areas left that I always have. And so I'm going to write some equations. All right? What is my blue Gatorade equation going to look like? 5 plus 11 29. Perfect. And then I got one for my red Gatorade. 31, that's what you use your totals for. And then 11 plus 2 plus y plus z equals 22. Right? So now we're going to clean up our equations. So let's see, this is 16, so x plus y has to be 13. X plus z has to be 10. Good. And y plus z, 9. Okay, now what did we say we were going to do next? Now you got boiled down to these equations, but now you need to solve them. So what are we going to do? Let's do the same thing every time so we never get confused. We're going to add the top two together and eliminate the only thing we can eliminate, which is the x, right? The one they have in common. So we'll multiply these by a negative. And when I add them, what am I going to be left with? These are gone. So y minus z equals 3. Then what? Okay, these equations I'm done with now, right? Because I've added them together, but I still have this one, right? So I'm going to put him up here, and what do I notice? Magically, what's going to happen? The z's are gone, so 2y equals 12. Which means y equals 6. So then I can go back to my Venn diagram and start filling in the sections that I didn't know what they were. So once I put a 6 in there, what do we know about the whole V circle? It equals 29, right? Well, how much do I already have? I have 5 and 6 and 11, so that's 22. So this must be 7. And then I don't care, one of these circles, like the whole W circle has to be 22. How much do I have already? 19, so that's got to be 3. And it's kind of a little check. This one's supposed to add up to 31, does it? Yeah. So there's your Venn diagram, completed. So now we answer the questions. How many athletes drink only blue and red? So only blue and red would be right there. 7 of them? Those are the blue and reds, 7. If I pick one, what's the probability he doesn't drink Gatorade? Well, wait a minute. Where are the people that don't drink Gatorade? They're out here. We got to figure out if there are other people out there. How do we figure that out? We got to add up all these numbers. And if there's 50 of them, then everybody drinks Gatorade. But if there's not 50 of them, then we know some of them don't. So what do we get when we add up out of every single one of these individual numbers? 44. So there's 44 people in the circles, which means there's 6 that don't drink Gatorade. So remember the question. The question is, reach in and grab somebody. What's the probability he doesn't drink Gatorade? That'll be 6 out of 50, which reduces to 3 out of 25. If one athlete is selected from the class, what's the probability that she will drink only 2 kinds of Gatorade? So what does that mean? You understand what that means? She drinks blue and red, or she drinks blue and white, or she drinks whatever the other combination is, white and blue. What's that going to be? aren't these the numbers we wanna add up? Right here? So that is what, 16 out of 50? Or 8/25. Once you get the Venn diagram completed, you can answer about every question that's asked. So all this work was getting the diagram completed. All right, you feel like you have a little better handle on that now than you did the last time
Yeah.
we worked together? We'll practice them again when we get to our practice test, which we're not even close to being ready for, so we need to find where we left off, get back to our regular notes. Don't act so excited. So I think we are on the back of page 14. And we're gonna roll 2 dice. Alright, so enough of the Venn diagrams for a minute. Now we're gonna go back, we're on the back of page 14, number 4. We're gonna roll 2 dice. And we wanna get a total of 3. Now, we're doing a probability question, so obviously it's gonna be a fraction, right? Let's start by trying to figure out the total number of ways that 2 dice can land. You know, like if you throw them, you can get a 5 and a 2, or a 6 and a 1, or, you know, what are the total number of ways 2 dice can land? Do you have any idea?
36.
Ah, 36. That's exactly right. Now, without writing out everything, let me give you kind of a little chart here. The first dice could land this many ways, right? Right. I'm not gonna fill this whole thing in, but I want you to kind of get a feeling for why it's 36. The second one could land this many ways. I mean, this is the first dice. It's either gonna be a 1, 2, 3, 4, 5, 6, and so is the second one. Okay? So one of the options would be I could get a 3 and a 4, right? This would be I get a 3 and a 4. And another option would be I would get 2 5s, right? And all of these boxes represent options, correct? Is it making sense now that I've drawn a picture of it? Well, how many boxes are there here? Yeah, because this one lands 6 ways, and that one lands 6 ways. So there's 36 options, okay? So what does that mean about my probability problem? It means my denominator is going to be 36. Now, what's my numerator going to be? All of the ways that we can actually get a 3. Okay, so think about it. Or use the chart since I've drawn this much of it. How could we get a 3? We could get a 3 right here, right? I'll put X's in them. That would be a 3, a 1, and a 2. 2 and a 1. Is there any other way to roll 2 dice and get a 3? I don't think so. So there's only 2 ways. So there's 36 total boxes, but only 2 of them give me what I want. So my probability is 2/36 or 1/18. What about a 7? What's my denominator? 36. That isn't going to change. Every time you roll 2 dice, your denominator is 36, if they're normal dice. Where can I get a 7? I'll put purple boxes in there.
2 and 4.
Red. I can get, okay, so here's 5 and 2, and here's 2 and 5. So 3 and 4, or 4 and 3. 6 and 1. Oh, look at this. They make a nice little diagonal, don't they? kind of cool. Are there any other ways up there to get a 7? No. Hey, remember we did 3? Did they make their own little diagonal?
Yeah.
What do you think this row would be? The 4s?
Yes.
And the 5s, the 6s, now we got the 7s going? All right, well, anyhow, I don't know if that's valuable or not, but we observed it. How many red X's do I have? 6? So that's 1/6 probability. And how about 12? Oh, 12's an easy one, I think.
6s.
The only way to get a 12 is to get a 6 and 6. So wouldn't that just be 1/36? That one's easy. So, drawing this diagram was helpful, wasn't it?
Yes.
We call this drawing the sample space. That is all of the possible outcomes. Do you have to do it? Absolutely not. Do you have to format it like this? Absolutely not. But when you're confused by something, try drawing a picture of it, because a lot of times that will help. Okay, now I'm going to have 4 children. I do have 4 children. And I want to know, what is the probability that I will have 2 boys and 2 girls? Now, we can take some guesses, and some of you might guess right, but I want to show you, before we run out of time, how we could draw a picture of this. So I'm going to have my first baby, and the options for my first baby are boy or girl, right? I mean, that's what happens. And then I have my second baby, and it can be, or he or she can be a boy or girl. So see what's happening so far is, this is if I have a boy first and a boy second. If I have a boy first and a girl second. If I have a girl first and then a boy, or if I have a girl and then a girl. Which, by the way, that's what happened to me, in case you care. All right. Then we have our next baby. It can be a boy and a girl. That's our third baby. See how we've had 3 now if you follow each branch? Girl, girl, boy. Girl, boy, boy. See how each branch gives an order, birth order? And then we need our 4th one, which would be boy, girl, boy, girl. Now, I am a huge fan of tree diagrams, especially when things are in order. Whenever I'm considering anything that's happening in an order, I like to draw a tree diagram. Now, what's the issue with a tree diagram? It gets really big. You know, if I had 12 kids, this thing would be huge. Luckily, I don't. So, here we go. Mr. Matthews has like 10, I know. Well, Levi Italic, I think do they have 10 or 12? They have a bunch too. Okay, now, I just want everybody to understand. This means I had a boy, then a boy, then a boy, then a boy. This means I had a boy, and then a girl. Right? So you understand? Now, what do I want to have happen? I want to have 2 boys and 2 girls, and I don't care what order they're in. So let's find the branches that have 2 boys and then 2 girls. Would that be one right there? I'm going to put a check mark at the end of it, because that's boy, boy, girl, girl. How about boy, girl, girl, boy? Girl, boy, boy, girl. Girl, boy, girl, boy. Girl, girl, boy, boy. Let's see, are there any more?
Yeah.
I don't understand.
There's one more.
Okay, I'm trying to get 2 boys and 2 girls. So, boy, girl, girl, boy. I'm just following the tracks. I don't want boy, girl, 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 because that's too many girls.
Too many.
So I'm picking the ones that have girl, boy, boy. That would be what I want. I want 2 of each. So I'm just trying to find all the paths that have 2 of each. I don't want anything down here.
One above the second check mark, isn't that one?
Above the second check mark, right here. Boy, girl, boy, girl. Yep, that would be another one right there. Now, another thing you can do, if you don't like the tree diagram, you could write out all the options and say, okay, you could have 2 boys and then 2 girls. You could have 2 girls and then 2 boys. You see what I'm doing?
Yeah.
I'm just writing out the possibilities. Instead of drawing them, I'm writing them out. So I could have girl, boy, girl, boy, girl, boy, boy, girl, and just write out all the options. I might as well, I'm almost done. Boy, girl, and boy, girl, girl, boy. I think that's it. So how many ways can I have 2 boys and 2 girls?
6.
6. So my numerator is 6. What's my denominator? Well, my denominator would be the total number of paths that there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So your probability of having 2 boys and 2 girls is 3/8. Now, I want to make a couple of observations here. The first one is, when we rolled 2 dice, how many total ways were there for the dice to land? What was our total? 36. Because the first dice could land 6 ways, and the second dice could land 6 ways. That's how we got 36. Now, I'm having 4 kids. There's 2 possibilities for kid 1, boy or girl. 2 possibilities for kid 2. 2 for 3 and 2 for 4. That's your total number of ways. If you multiply up the number of ways each event can happen, that gives you your total. Okay, so who had a question over here? Someone had a question.
You answered
I
it
did?
just now.
Okay. Now, Stuart, are there 4 of you guys? 4 boys? Okay, so they had 4 kids, all boys. What's the probability that that would happen? If you said, my goal in life is to have 4 sons, what's the probability that will happen? There's only one way to get all boys, guys, and it's right there, right? So the probability of all boys would be 1/16. That's it, 1/16. What's the probability of all girls? Same thing, right? And then all the other combinations we can figure out. Perfect. All right, well, I'm gonna have to erase that to get going on the next one. Anyone have a question about that? Okay, so now we're gonna look at a little bit of official Venn diagram notation. So this is not a problem. This is just a way of getting used to the notation. So you need to draw this picture. Well, I drew it for A, but you're going to need to draw it for B, C, D, and E. And we're going to shade in what this says. So the Venn diagram is drawn for you, and your job is to shade this. What is this saying to me? Do you happen to remember from geometry class? Nope, don't remember anything from geometry class. This is the symbol for intersection. That is the math way of saying overlap. So if we are going to shade the intersection or the overlap, what are we shading? Just this part right here. When we read this, we say P and Q. Those are the people that drink red and blue Gatorade. Or those are the people that like brownies and cookies. We say and. That means overlap. Now the next one, you need to draw your own diagram. I got lazy and said I'm not going to draw this, but you need to draw that for every part because you're going to shade something different in every part. B says we're shading P. So what are you coloring it? Are you coloring just this part? No, you are coloring the entire P ball. The entire P ball. That's like saying these are the people that like pancakes. All these people like pancakes. Now, these guys might like waffles too, and that's fine, but all these guys like pancakes. So that's what we shade. What about the next one? Anybody remember what this means? We have used that symbol in this class. Anybody remember what that means? Or, remember when we used interval notation, we had to use that symbol, but if we wrote it out by hand, we said x is greater than 3 or x is less than 7, something like that, right? So this means I want to shade everything that's in P or Q. So I'm going to shade everybody that likes pancakes and or waffles, either one. So what am I shading in? Everything in the circles. Yep, not the outside part, but everything in the circles. Those are all the people that like pancakes or waffles. Now, do some of them like both? Sure. But everybody up there likes pancakes or waffles. And then we take a wild guess what that means?
Without the intersection.
This means not P. The math word for it is the complement, but it means everybody that doesn't like pancakes. And that's everybody that doesn't like pancakes. So where would I shade that? That's everything except the P ball. So the entire box is shaded. The only thing that's not shaded is the P. It's okay, clock watchers. It's all right.
I'm starving.
Well, and you don't get to eat yet because we got the assembly for it.
Oh, I've got.
So you're just gonna have to starve. Oh, I forgot to get my snacks out.
You just have to start.
Too late now.
I'll pay you, Mrs. Ford.
I do have some cookies for sale there.
How much?
They're 3 for 50 cents.
Oh, that's not bad at all. I got you.
Too bad? That'll be $1.
I got you right there.
Okay? What does this mean?
The outside.
Well, tell me this. What does that mean?
That means the intersection.
That means the football, right? Kids? That means the football. So what happens when I put that mark on it? Not the football. So you're going to shade everything except the football, and that includes the ins and outs. Oh, all of a sudden it's brownie.
Oh. You guys are so mean. None of y'all was worried about it until I asked.
Okay, here.
It doesn't even want it anymore. That is so.
That's what you give me taking so long.
No, it's okay. I don't want it. I wanted a cookie.
These are cookies.
No, it's okay. I like the M&M ones. It's fine.
Okay. All right.
Oh,
So, I want to back up. This problem right here, guys, listen. When you have to shade something that's a little more complicated, do it a piece at a time. Everybody knows, or should know now, that this means the overlap, the football. So if you think football, that means not. So you're going to shade everything that's not the football. So that's why that's shaded in. Okay? All right. Let's see. All right, so we'll pick up with 15 next time. Now, here's what we're going to do. We're going to leave our stuff here. Yes. We got directions this morning. We got to leave our stuff here.